De Moivre's theorem. Raising a complex number to a power is also easier when the complex number is written in polar form. Property 4, De Moivre's theorem. Cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. Or kis theta to the power of n is equal to kis n theta for n elements of the rational number set. I.e., we can raise a kis to a power by multiplying the angle by the index. The proof of De Moivre's theorem for n elements of the natural number set is on our course. This proof makes use of proof by induction. This is the proof of De Moivre's theorem, and it will be covered in a proof by induction video. For now, we will just look at how to use De Moivre's theorem. So even though we only proved De Moivre's theorem for n elements of the natural number set, we can still use it when n is any rational number. Thus, for example, cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. So example 1, cos theta plus I sine theta to the power of 4 gives us cos 4 theta plus I sine 4 theta. Example 2, cos A plus I sine A to the power of minus 2 equals cos minus 2A plus I sine minus 2A. And example 3, cos x plus I sine x to the power of a third equals cos third x plus I sine third x. Example, evaluate cos 45 degrees plus I sine 45 degrees to the power of 8. So cos 45 degrees plus I sine 45 degrees to the power of 8 is equal to kis 45 degrees to the power of 8, which equals kis 8 times 45 degrees by De Moivre's theorem, and 8 times 45 is 360, so we get kis 360 degrees, which breaks apart to give us cos 360 degrees plus I sine 360 degrees. Cos 360 degrees gives us 1, and sine 360 degrees gives us 0, so we get 0y. So the answer is actually just 1. We only have a real part in our answer. So we used De Moivre's theorem for this step here, which is stated above. And make sure that you use degree mode when you're using degrees. Example 2. Use De Moivre's theorem to write cos 2 theta plus I sine 2 theta to the power of 3 divided by cos 3 theta minus I sine 3 theta to the power of 4 in the form of cos alpha plus I sine alpha. So first we're going to rewrite cos 2 theta plus I sine 2 theta to the power of 3 as kis 2 theta to the power of 3. And we're going to rewrite cos 3 theta minus I sine 3 theta to the power of 4 as kis minus 3 theta to the power of 4. Next we use De Moivre's theorem, which is stated above. So we're going to multiply the power by the angle. So kis 2 theta to the power of 3 becomes kis 2 theta multiplied by 3. And kis minus 3 theta to the power of 4 becomes kis minus 3 theta multiplied by 4. 2 theta times 3 is 6 theta, so we get kis 6 theta as our numerator. And kis minus 3 theta times 4 gives us kis minus 12 theta. So we get kis minus 12 theta as our denominator. And we know from our kis properties that when we are dividing two kisses, we subtract the angles. So we're going to have 6 theta minus 12 theta gives us 6 theta plus 12 theta, which gives us kis 18 theta. And breaking this out gives us cos 18 theta plus I sine 18 theta. On an argon diagram, successive powers of a complex number z cycle about the origin. If the modulus of z is greater than 1, then the powers spiral away from the origin. So for example, here's the origin. So this is our real axis, this is our imaginary axis, this is the origin, and this is the complex number z. For example, if z is equal to 2 kis 45 degrees. So let's say that this complex number z is equal to 2 kis 45 degrees. So it has a modulus of 2. Then z squared is equal to 2 kis 45 degrees squared, which is going to be 4 kis 90 degrees, because 45 times 2 is 90, and 2 squared is 4. And z cubed, which is 2 kis 45 degrees cubed, will give us 8 kis 135 degrees, because 3 times 45 is 135, and 2 cubed is 8. And z to the power of 4 is 2 kis 45 degrees to the power of 4, which is 16 kis 180 degrees, because 45 times 4 is 180 degrees, and 2 to the power of 4 is 16. These points are shown opposite. So z is 2 kis 45 degrees, which is here. So it has a modulus of 2 and an angle of 45 degrees. Z squared is 4 kis 90 degrees, so it lies on the imaginary axis, which gives us a 90-degree angle. And it has a modulus of 4, so it's got twice the modulus that z has. And z cubed has a modulus of 8 and an angle of 135 degrees. So from the real axis going anti-clockwise, we have an angle of 135 degrees on a modulus of 8. And z to the power of 4 has a modulus of 16 and an angle of 180 degrees. So 180 degrees starting at the real axis and going anti-clockwise, we end up on the real axis, the negative part of the real axis, and we end up at 16 units. So technically this is minus 16i, this point here. So we can see that what's happening is the z's, the successive powers, are spiraling away from the origin. If the modulus of z is less than 1, then the successive powers of z spiral towards the origin. If the modulus of z is 1, then the powers of z rotate about the origin but lie on the unit circle. And that is because whether we square 1 or cube it, it will always still just be 1. So it doesn't matter what the power is, the modulus will continue to be 1. Because 1 to the power of anything is 1.